just for this week. And yeah, so just for this week, I'm recording sessions and uploading them, which I have started doing right now. And just to remind you guys, I don't know if you guys get these emails or not, but I made an SI announcement. So if you didn't make it to the exam review on yesterday, on Sunday, then I posted a link to the actual exam review right here. So you go to my SI website, and then you'll find the actual video. So it's right here. I'm going to put it in the chat in case you don't feel like Googling it. So there's the link to the video in case you need to go back and check on that. Do I think that the problems from these old exams are pretty similar to current questions? Yes, they tend to be very similar in content, but since the course is online, the pace is different. They're probably going to squeeze some extra content in. So the difficulty and content of these questions are very comparable to this exam, but they're probably going to squeeze in a few more things. So they'll probably cut out some either easier or more difficult, depending if they're feeling charitable or not. They'll probably cut out some questions, probably about rotation, because and momentum. Momentum is for some reason a huge component of this test specifically, and I don't really know why. And to answer your question, Tyler, yes, this is a torque problem. So, I've talked for 2 minutes. We'll do an icebreaker. Yesterday, I asked you what your favorite Thanksgiving food was, so let's narrow that down. What is your favorite kind of pie? You know, keeping with the Thanksgiving theme, it's an excellent holiday. What is your favorite kind of pie? I mean, I know that was discussed yesterday, too, but I'm not feeling particularly creative right now. That just came up with that off the top of my head. French silk, that's a good choice. See, someone enjoys pumpkin pie. Pumpkin pie is very good. So I don't remember who said it yesterday, but someone said that pumpkin pie is trash tier pie. And I was just appalled at that. Okay, for those of you who said apple, how many of you appreciate the cheese on apple pie? The cheddar cheese. Because I have tried that, and I gotta say, it ain't bad. Get a nice slice of apple pie with a nice sharp cheddar on there. It's pretty good. Only 3 types of pie in your entire life. You gotta expand your March 14th, you guys. March 14th, go buy yourself a slice of pie from Perkins, anywhere. Do that. Pie Day is an excellent time to eat pie. Answer to your question is yes, Tyler. All right, pretty good responses. All right, yeah. I don't think there's much more to say about pie. But yeah, November 14th is, not November, March 14th is Pi Day, you know, the best math holiday. And also, it's Einstein's birthday, funnily enough. So, want a little trivia fact, that's a little tidbit of knowledge. Einstein's birthday is on Pi Day, which is very appropriate. He did so much with math, and then all of general relativity is really, it's in the language of tensors, but it's really just differential geometry. And, pi is intimately related to geometry. Anyways, that's enough trivia and pie talk. Does anyone have any questions before we get started here? Okay, doesn't seem like it. That's fine. So we can get started at number 11. So I believe this is where we left off yesterday. If not, please let me know, and I will scroll back to where we did leave off. But yeah, so what we've got is it's very confusingly worded because we have a pulley and a mass attached to that pulley. The question is asking what is the acceleration of the mass in meters per second, and the pulley, we know the radius and the mass of the pulley. But keep in mind that this big M is 4 kilograms and this little m is 5 kilograms. So they mislabeled things, right? Usually big M is the bigger mass. Not in this case. This pulley has less mass than this block right here. All right. So as usual, if you guys are you hit a sticking point, I suggest you try and approach this problem by yourself for like the first 2 or 3 minutes. But if you're completely stuck, don't know where to go from there, um, then I would like you to tell me, and then I can give you a push in the right direction. But like I always say, drawing a picture is a good idea. Even though we have a picture of the situation right here, drawing that picture yourself allows you to manipulate things and label things the way you want to, and it's very helpful. If you guys can put your net IDs in the chat, that would be appreciated. I'm gonna see if I can't do this during the session. Take 10 minutes, that is. Can someone answer me the question of when your test is on Wednesday? Because if it's after or if it's before the session, okay, it's at 7:30. Excellent. That means that I will be going right up to the dot with my regular session time. Because remember, Wednesday session is at 6:30, not 5:10. So, yeah, regular time. Can't believe I messed that up in the announcement. I will be proofreading much more carefully next time I post something to the entire class. All right, yeah, so thank you guys for putting your net IDs in there. And watch. Okay, someone's already got an answer. They got D. So I'm not going to confirm or deny if that's correct. But hey, if you got an answer that's on the that's one of these 5, that's pretty good.
I have a quick question about this one. So I asked you if it was going to be like R cross F equals I alpha, and you said that was like what it was. So wouldn't the accelerations cancel out because it would be R times mass times acceleration, so it'd be RMA equals I alpha, and then alpha is equal to A over R. So if you divide both sides by A, then the A would go away.
Yeah, so you can do that, and if you cancel out the A, then you can back substitute the number that you get for the tension, and then solve for A that way.
Oh, so, okay. So I think I was forgetting the tension in this problem then.
Yeah. So if you go about solving this algebraically, there is a way you can cancel out A, but then you just end up solving for a different thing, and then you can plug that different thing back in and solve for A that way.
So where's the tension come in on this? Is it going to be like the RMA minus T equals the I alpha?
Mine, not quite. Think about how this pulley rotates, what is causing that rotation, and how that rotation is related to the forces on this block. Yeah, and then if you sketch out 2 FBDs for both of these objects, then you should be able to figure out where the tension factors in from there. That's okay, Christian. Even if you did it wrong, I appreciate you putting your answer in the chat. That's very brave. Because I know many of you guys do get answers and don't want to put them in the chat. And I like it when you guys put answers in the chat, because then I can give you guys feedback. Okay, someone else got C. This is good. Try and discuss amongst each other. I'm going to try and put this attendance in. Okay, Dylan is stuck. So, like I said, thinking about how the tension and drawing FPDs is a good idea for starting this problem. This one is tricky. I worked on this problem and I made a really silly mistake when I was working on it, and it took me like 10 minutes to figure out where I made it. At least 10 minutes. It took me a while. So, when you're doing this problem, the way I always approach these sorts of things, so this is a very common problem where we have a pulley and a mass hanging from that. And then we were asked, okay, let's describe the motion of either the mass or the pulley, right? Because they're very, very well connected. So let's read the question carefully. We have a box, it's got some mass, and it's attached to one end of the string, and the string is wrapped around the pulley. The pulley is treated as a uniform disc. The string does not slip. So that's an important note right here. The string does not slip on the pulley when it's going down. So that means that the rate of rotation of the pulley and the rate at which the mass is falling, those two are the same. Or at least they're related. They're not exactly the same, but they're well related. That means that for every one rotation that this pulley makes, then this string has dropped a full circumference, right? Because there's no slipping, which means that each rotation just corresponds to the distance that string is wrapped around the circle. So that's an important point. And that means that we can translate between the rotation and the rotational motion and the linear motion of these two objects. We know that this thing is going to be spinning, and we can use the fact that r times alpha is equal to a to put this rotation in terms of the acceleration that we're trying to solve for. So that's one point that we need to solve this problem. And the other way to begin solving this problem is we draw an FBD for this mass right here, and then we draw an FBD right here, but we know that this thing is not moving up or down, right? So that means that MA is going to be equal to 0. There's no linear acceleration happening here, so we have to think instead about the torques to describe the rotation. So instead of saying F equals ma to this, we're going to say that torque is equal to I alpha. So if we can describe what the torque is, then we'll be in a good spot. So can anyone answer the question, what is causing this thing to start angularly accelerating? What's causing the rotation of the pulley?
It's because the block's pulling it, right?
Yep, that's exactly right. It's the torque due to the block. So if we can describe that force due to the block, then we'll be yeah. So Christian, the answer isn't incorrect either, but it's not quite g, right? Because it's the force of this block. So we need to multiply that g by m to get the right answer. But there's even more of a caveat to that, because this m is accelerating downwards, right? This wouldn't be a very interesting problem if 0 was an answer here. So it's accelerating downwards, which means that the tension is not the same as gravity here, and we know that from the FDE. So there's a lot of parts to this problem. So I'm going to give you guys some more time. Hopefully that clarified a little bit. But the key point here is translating between these two different objects. So we can set up an FBD for this, and an FBD for this, and then there's something that ties them together, and that something is tension. From there, you can work with the algebra. You get 2 equations and 2 unknowns, and you can work with the algebra to solve for A. I gotta go back to.
So I do have a quick question. It's about the tension of the rope and the torque on the disc. I have a lot of trouble just seeing, like I know that they're related, but I'm not exactly certain how. You know what I mean? Like what's the exact relationship between them, and how can I turn that into like an equation?
That's a very, very good question. What does your intuition tell you? Like, if I asked you without thinking about it, what is the relationship between the tension on the pulley and the tension on this mass right here?
Well, I would probably say something along the lines of it's something with the radius, like times the force going down. Because it's not all directed downward, right?
Well, actually, no, it is. It is. So the answer to your question, how is the tension on the pulley related to the tension on this mass here? The answer is that they're equal. They're the same tension, and they both act pointing but they're in the third law pair. So the tension acting on this object right here, the block, the tension is pointing upwards for that block, but for the pulley right here, the tension is pointing downwards, and it's pointing downwards at a distance of r tangent to the circle at that point. So
Okay, and that works for the torques too?
Well, no. You know how to describe the force, and now you need to translate that force into torque. So how do we do that?
Okay. I don't know.
Okay.
That's got something to do with the radius, right? It's like the distance from the center of mass times the force, right?
Not necessarily the center of mass all the time, but in this case, yes.
Okay.
Cool. And to be perfectly general about it, the torque due to any force is just the distance that force is from where that thing is rotating. So for our case, it's going to be r. Then that's got r as a vector, and then you cross that vector into the force. But in our case, the cross product is really easy to do since these two vectors are perpendicular to each other. So r is pointing from the center to here, and then t is pointing downwards, so that there's a 90-degree angle between the two. So then our cross product just becomes the magnitude of the product of each magnitude. So it's just how big is r and how big is t.
I just realized that I was unmuted this whole time. I'm sorry if you heard. I'm sorry if I made any noises that distracted.
You're good.
I just realized that I was unmuted.
No worries. Happens to the best of us. Okay. Where did I leave off in attendance? I think that's. How are we doing on this problem? Do we have answers? Are we still struggling? Okay, that's attendance taken care of. Wow, there's a lot of you today.
Yeah, I thought I had it for a second, then I got stuck again. So.
All right. So it's already 4:50. Let me pull up the notebook and try and set up the problem so that you guys can. I for a disk is 1/2 times the mass of the disk times the radius of the disk squared. I'll pull up the notebook and then set it up so that we have a better idea of how to start the problem. So let me get the notebook set up. And just for reference, if you guys are looking for, if you ever forget what the moment of inertia is for something, it is just the, it's on your equation sheet. And you just use the parallel axis theorem as needed. Come on. There we go. Okay. So, we are doing problem 11 right here. So the way to start this is by drawing a picture, right? So, but we're gonna sketch out the picture. Actually, I'm gonna skip drawing the picture. I'm just gonna draw the FPDs since they give us the picture here. So we're gonna start with a simple FPD. So we're gonna label it as the mass, right? The hanging mass. We're gonna draw an FPD for that. So we treat it as a point, and we sketch the forces that are acting on it. Well, there are only two, right? So it's not moving side to side. There's no net force acting there. Nothing confusing there. And then it has a weight of mg and a tension pulling it up. This tension is going to be the key between translating between the disk and our mass here. So then, if we sketch what's happening on the disk, we have to be careful because the net force on the disk is 0, right? You know, it's not accelerating linearly, so that means that the forces must add up to 0. So the tension is going to be pulling it down, but it's pulling it down at a radius of r, and then the thing that's anchoring it to the wall is pushing it up with the same magnitudes. That's why the pulley doesn't go up or down. But we don't care about describing the up or down motion of the pulley. We want to describe it spinning. So what we're going to do is draw it as an extended object, not a point. And we have a tension pulling it downwards. It's the same t as in the other diagram. And then we sketch out the radius and label its mass. So that the mass is big N. Okay, so this is what we've got right here. So from this mass, we can easily set up an equation using Newton's second law. So I'll set up that equation since it's pretty easy. So we say that little m times a is equal to, okay, we're going to call downwards positive. That's the part that tripped me up in this question because you need to make sure that you're consistent among your reference frames to get the right answer, or consistent with your directions is a better way to phrase that. If you're consistent with the directions, which way is positive, then your answer will work out correctly. If you're not, then you're going to get minus signs where you should. So if you say that downwards is positive, then mg is pointing in the positive direction, t is pointing in the negative, so you subtract off t. So we're trying to solve for a. We don't want to cancel a out in our expression. So we want to figure out an equation that describes the rotation of the disk, and we need to figure that out in terms of a. So I'm going to give you guys here. Actually, I'm just going to ask: would you guys rather I finish the problem right here? We've already spent quite a bit of time on it, or do you guys feel like you can get an answer? Finish it. Two people say finish it. One more, and I'll do it. Okay. So we'll just run through it then. Okay, so to describe the motion of the disk, we know it's not moving up or down. We know it has a net torque on it. So we're going to say torque is equal to I times alpha. There's nothing complicated with I, it's just a disk. So it's 1/2 m times the mass of the disk times the radius squared. 1/2 mr squared, big N. So we need to figure out what the torque is. So let me just be extra clear here. This is like a separate thing. Torque is equal to I alpha. If we want to figure out what the net torque is, we need to think about all the forces that are acting. Well, there's only one force that's acting with the distance from the center of from the pivot of this disk, and that's T. So, like I said, T is acting perpendicular to this radius, so the cross product is nice and easy to evaluate. But I'll just be extra clear. So T is R cross F, which is equal to I alpha. So R, in our case, we can rewrite this. There's an identity on the first page of your equation sheet that says that the cross product can be rewritten, more specifically the magnitude of the cross product. So when you take the cross product of two vectors, you get out another vector. But when you, if you only care about how big that vector is, then you can say that the value that the cross product gives you is R times F times the sine of the angle between the two. is equal to I alpha, but we know that the sine of the angle between these two vectors is 90, right? I said that these vectors are perpendicular, so this sine is going to be 1. Sine of 90, that's 1. So what is f? It's just, I'm gonna change this to big R. So f is just t, right? That's what we said. Okay, so that's equal to this. Let's slot in our moment of inertia for a disk. 1/2 big M big R squared times alpha. Okay, so what we want to do, yeah, I know, is actually put alpha in terms of A. We're trying to solve for A, so that's what we're going to do. So we're going to use the fact that our alpha is equal to A, so that means that alpha, okay, yeah, sorry, I got confused. Alpha is equal to A divided by R, so then we plug that in for alpha. So we just plug in A divided by R. So we can cancel out an R right here. That one is confusing. Let's move it over here. Cancel out an R there, an R here. And we find out that T, our tension, is equal to 1/2 times M times A.
Hold on, where did you get R alpha is equal to A again?
That's on the circular motion portion of your equation sheet.
Okay, that's what got me stuck, sorry.
Yeah. It takes a bit of practice to get used to translating between the two, but if you ever forget, the way I remember is if you have a circle and you care about describing this length here, well, this is theta, some angle there. If you care about describing how long that is, then that arc length, the arc length formula is just R times theta is equal to this distance S. And then you can take the derivative of that to find the other things. But if you don't remember that, that's fine. It's on your equation sheet. And then we're going to plug this in to our equation that we have right here. MA equals mg minus t. So if we plug that in, we have m times a is equal to mg minus 1/2 big M A. We want to solve this for a, so how do we do that? Nope. We do that by moving over the a and factoring it out. So we get a times m plus 1/2 big M is equal to mg. So we divide that over, and we get a is equal to mg divided by little m plus 1/2 big M. So we can plug in all these numbers. That's all given in the problem. So when you do that, you end up with a value of 7. Nice clean value of 7 meters per second squared, which is C. So that was a tough problem. I'm not gonna lie. It took a bit of algebra to get there. But the key point, right? All of this is just math. All of this part that we worked through, almost all of it is just math and slotting in equations. The physics of it is setting up these diagrams right here. If we can set up these diagrams and figure out what these diagrams are telling us, then the rest of the problem is mostly straightforward. So whenever you have this sort of thing where you have one object and another object, and they're connected by like a string, then usually it's a good idea to draw an FBD for both diagrams, and then figure out, well, the tension is the same, or something is the same between the two, and that's how you describe how you translate between them to solve for a quantity.
Why do we multiply by acceleration over alpha?
Because we are translating, we have alpha there. Wait, why do we multiply by acceleration over alpha?
Or I mean over R, yeah.
Oh, yeah, so we're doing that because we want to put our alpha in terms of linear acceleration. So if you have a circle that's rotating, then like this distance you can put in terms of the rate at which it goes through that angle theta, and it's like translating between s and delta theta. What is the relationship between those two? Does that make sense? Is that a good way to explain it? Okay. So let's move on to the next problem. So this problem also not super easy, but what we've got is a bar with the mass hanging from it, and then tension is pulling it towards the bar, and this bar is attached to the wall by like a hinge or something. So the question is asking for what is the tension in the cable, and we know what the mass of this rod is and what the mass of this block is. So yeah, I hope I remember to clock in. I need to double check that. So if you're completely stuck on where to start, I forgot to clock in again, then this is a statics problem. So I'm just going to tell you that. Nothing is moving. That's static means not moving. So it's a statics problem. And how we approach statics problems is we say F equals ma is equal to 0. Sketch out where the forces are. We say F equals ma is 0. If that doesn't give us any useful information, then we say that the torque is also 0, right? Because we're not moving, we're also not rotating. That's the key point. Okay. So 11 and 12, probably one of the harder questions on this exam. So I finished the exam today, and I think that the questions from here on out get a little easier. So we should be able to finish this on Wednesday, but we'll see. And it's hard to tell sometimes.
I have what you might call a really stupid question.
Bring it on.
So the box has 30 weight, and that 30 would be pulling down, right?
Yes,
So if it's not moving, then there should be 30 pulling up, right?
that's exactly correct.
So then how come the tension isn't 30?
Because this tension is not holding up just the box.
Okay. Sure. Thanks.
Yep. Okay, so we got B. Is anyone completely stuck? Okay, if you're complete, okay, if you have an FDD and that's it, that's a good place. That's a good place to be. So my advice to you is ignore the F equals ma for this, right? So when we're given a statics problem, you can always say that F equals ma is equal to 0, but sometimes that doesn't give you a very useful idea of what's going on, or it doesn't give you what you're trying to solve for. So let's read the problem and focus in on what we're trying to solve for. Uniform beam, 20 newtons, 30 newtons, attached to a cable, angle, information. Okay, horizontal cable connects the beam to the wall. What is the tension T in the horizontal cable? Okay, so we're trying to figure out what T is. If we want to figure out what T is, I'm going to tell you now, you only need one equation, and that the equation is the torque equation. So if you add up all the torques that are acting on this bar, then you'll be able to solve for T from that. And you might be confused that they don't give you a length. They don't give you the length of this rod. That could be confusing. I say you just call it L, and you'll see that it should cancel out of your equation. Or if you want, you can say length is 1 without, and then just, multiply by 1. You're technically allowed to do that, but I think that's sloppy. Though that's what we do as physicists all the time. There's a whole name for it. It's called natural units. If you go deep into physics, you get like, you talk about how fast you're going in terms of c. Well, c is 1 if you're using natural units. So it's like multiply by c. Or if you're doing quantum, you say h bar is equal to 1. And then it's like just multiply by h bar whenever you want to get units to work out. But this is 221, not 362. So don't use natural units. That's the point of that.
You promised me peace. That's all I could wish for. All I need. Time to take the power back, strap into driver's seat. I ain't gonna let you ruin me. You won once, better enjoy it. Cause no one's once, don't get used to it. Start saying bye bye bye. You better hope you don't cry me a seat. Remember when I saw you as I drove by? I was thinking why you gonna mess with me when I'm so loyal to what we could be? Everything feels so wrong.
So 2 people have answers for this one. Has anyone else finished? Because I'd like to go through this at like 5:10. Okay, so it doesn't seem like anyone's finished, but would anyone like to, is everyone okay if I go through it at 5:10? Can we do it now? Yeah, we can go through it now. Yeah, we'll keep the pace going. Okay, so let me pull up the iPad. Yeah, no problem. I appreciate someone just someone giving me feedback. It's the worst when I just stare at the chat and no one says anything. It makes me very uncomfortable. Though I know you guys are just working hard. Okay, so we're doing number 12. The way we do this problem is by sketching it out, as usual. So let's do that. This is our wall, and we have our rod, it's pointing up, and then we have this cable pointing it this way, and then we have our mass that's sitting right here. So what I'm gonna do is label this as a generic angle theta, and then I'm gonna sketch where the forces are acting on my thing. So I'm gonna call this little w, and I'm gonna call this big W. This has a big weight of big W. And then we have tension right here. That's our end goal, to try and solve for tension. And so the geometry works. I'm being sloppy with my thetas here. But it's not really important because it's a 45-degree angle. So technically it should be 90 minus theta where the t is. That angle should be 90 minus theta, but since theta is 45, it's the same. And so I know that this angle by the little w is theta because it's a vertical angles right here. So the w is parallel to the wall. So you got a line that cuts through 2 parallel lines. And the angles must be equal. So that's how you figure out the angles. And now we're going to use all this fact to set up an equation that tells us about the torque. I know that small w is at the middle of the rod because that's the center of mass of the rod, and gravity always acts at the center of mass of an object. So if you're ever doing a torque problem and you need to know where that gravity is acting, then if gravity, you can always say, is acting at the center of mass of that object. That's a very good question. So now if we're pivoting about this point, so technically, just to be clear, there are forces that this wall is exerting in this problem. because it says that the wall is attached, that the rod is attached to the wall. So there's technically a normal force that the wall exerts in the y direction and a normal force that the wall exerts in the x direction. So those exist, but they don't end up factoring into this problem. You don't need to know them to figure out what T is. But they're there, they're keeping the rod from slipping into the wall and slipping down the wall. But the point is, if we choose our pivot to be right here, then the radius of these forces is 0. Our pivot is right here. That means that they have no radius to exert any torque on the rod, which means that the torque they exert is 0. So we're going to ignore those, and then we're going to think, okay, little w, the torque due to that is going to be little w times the sine of theta times L. So I'm going to call the length of the rod L. We don't know what it is, so hopefully it'll cancel out. Fingers crossed. Just double checking my work here. L over 2, sorry. That's because it's halfway up the rod, right? So that should be L over 2. So the whole length of the rod is L. We're not thinking about the X direction here, it's just the whole length. So that's the first torque. And then I'm going to tack on a minus sign because I'm going to say that the direction, if it's pulling the rod downwards, I'm going to say that rotation is minus because it's going into the page here. So we tack a minus sign on there, and then we think about the torque due to big W. Well, the torque due to big W is going to be minus big W times the sine of theta. Yep, so this is also theta right there. The same vertical angles again. Sine theta times L this time, and then we also have the torque due to T, right? So that's what we're trying to solve for. No, that theta should be attached to sine. Sorry, here, let me make my work a little clearer. And then we have T sine theta L. It's exactly the same, just on top of the rod. Okay. So now we just do some algebra to this, and hopefully we can see that L cancels out, which is good because we don't know what it is. So if we move over the negative terms, little w times the sine of theta times L over 2 plus big W times the sine of theta times L, well, that's equal to T times the sine of theta times L. Okay, so there's an L in each one of these terms. We can safely divide by it. Get rid of it. Awesome. And now, well, there's also a sine of theta in all of these terms. So we can get rid of that too. That's not true in general, since we use the fact that theta is equal to 45 here. So be careful, but in this case it works out. So we end up with W, and I forgot, W over 2, little w over 2, plus big W is equal to tension. So we know what both of these numbers are. Little w is 20, big W is 30. So we get 10 plus 30 is equal to T, which is 40. Let me double check that I did the math right. Yeah. Okay, which is B. That's B in case. Minus big W? No, because we're taking this equation. Because, yeah, so we got a minus sign right here. So when we add that over, the minus sign goes away. Anyone else have questions, or does that make good sense? Okay, no one's saying anything, so I'm gonna assume it makes sense. On to number 13. This one's a little bit more straightforward. Just need to be a bit careful. Yeah, so what we've got is an object with a certain mass. It's thrown upwards with the speed of v. We're looking for what v is because they know. Oh, yeah. So we're looking for what v. I was looking at the wrong problem. I know. Yeah, we're looking for what v is, and they give us a bunch of other numbers. So notice that we're not on Earth. That's an important fact. We're not on Earth, so we're given different values for mz and rz. This iPad is on 7%. Hope it makes it to the end of the session.
Is this a fatal attraction or something brand new? I got a strange emotion. Do you feel it too? Tell me what's on your mind. Used to be perfect strangers. Maybe I fell for you. Maybe it's nothing major. Just trying to speak the truth. What's love? What's love gonna do with us? Been having these conversations. There's something about you, more than just undercovers. I can't forget you. Tell me what's on your mind. Used to be perfect strangers. Maybe I fell for you. Maybe it's nothing major. Just trying to speak the truth. What's love? What's love gonna do with us?
Okay, so Tristan got A. The answer to your question, Dylan, is yes. Yeah.
Just a quick question. When we're using the equation for finding the gravitation, are we supposed to use the radius of the planet in meters or kilometers?
Meters.
Okie dokie.
Yeah. Good question.
Used to be perfect strangers. Maybe I fell for you. Maybe it's nothing major. Just trying to speak the truth. What's love? What's love?
I think 2 more minutes should be good for this one, even if you're not done. I hope to get to problem 15 by the end of the session. Because 15, I don't have any work written down, so it should be a nice conceptual problem to end on. Here's an idea, you guys. What if a certain number of you guys get A's on this exam? I'll do the next session in my Pepsi Man morph suit. Or not next session, not Wednesday, but you know what I mean. You get a little bit of a motivation. Would that motivate you guys? There will be no A's, sadly. Not with that attitude, Tyler. Come on, you guys. What did I say about having a positive attitude? One person. Holy shit. Okay. Maybe you're right. Man, I'd be a great high school teacher. Wait, there's only 27 questions. How is it out of 81 points? Why is each question worth 3 points? That's just evil. It's all worth it. Man, it's been a long time since I've taken this course. I'm gonna run through this. I don't want to get too distracted. Is everyone okay if I do that? Oh, I thought, Christian, I thought you said you were the one who got the A, and I was impressed. Okay, someone said yes. So I'm gonna run through this. I'm not gonna tell you if it's the right answer. A is correct or not, just yet. So this is problem 13. Oh, yeah, there we go. Okay. Problem 13. So I'm gonna pull up the iPad. Probably help if you guys could see it. So what we want to do is start by finding out what the gravitational acceleration is on this mystery planet that we're on, and we got a nice formula for that. So we know that G is equal to big G times the mass of whatever planet we're on divided by the radius of that planet. So we'll call that RZ, right? So that's going to give us G sub Z. So, where do we go from here? Well, the question, they give us the maximum height, right? So the maximum height, if you throw it up, and we're looking for the initial speed V, that's what we're looking for. So that's just a nice, simple conservation of energy problem, right? Because you know what the maximum height is, and all the kinetic energy that you gave at the beginning of your throw has been turned into gravitational potential energy, and we know what that gravitational potential energy is. We just figured out what it is, but we just have to be careful by plugging in GZ instead of 9.8 for our regular G. So, for math, that's just saying 1/2 m v squared is equal to m times g sub z times the height that ball reaches. So, we can cancel out the m's. It doesn't matter how heavy that ball is. We want to solve for v. So all we end up doing is rearranging this a bit. We get v is equal to 2 times gz times h, all under a square root. So if you want to be fancy, you can plug these terms in to your square root. You get a nice complicated looking formula. But you don't have to, because this number is readily calculable. And when you plug in the numbers, you should get an answer of 29.8 meters per second, which is A. So A is correct. Kept you in suspense there. Okay, we got 6 minutes. Big G is not 9.8. Big G is something times 6.67 times 10 to the negative 11, and that's on your equation sheet under the gravitation section. Yeah, so make sure you have that distinction, because they're definitely different. We probably only have time for number 14, so we're probably not going to get 15. That's okay. So this one is tricky. But it's a good problem. It's about as tough as these gravitation problems can get, without making you do some nasty integrals. So what we've got is a satellite with a certain mass, and it moves in a circular orbit around Earth at a certain distance above the Earth's surface. So we want to figure out what the period of the orbit is in seconds. So this one is tricky, and we only have 5 minutes, so I'm not going to try and I'm not going to wait too long before I give you guys hints. I'll start by saying this problem is actually, you just need one formula to solve it, but you can solve it in other ways that are more intuitive. It's just, you have a formula at your disposal that gives you the right answer. You just need to figure out what one quantity to plug in is. It's okay that you got the session time wrong. I'm recording this, so it'll be on YouTube. The next session will be on Wednesday at 6:30. So 6:30 to 7:30, right up to the time of your exam start. So Tyler, the answer to your question, I'm not sure how to answer it without like completely giving it away. Think. Think about what forces are in that system and whether or not they form pairs. See if that doesn't help at all. Tristan, to answer your question, you shouldn't need to get the acceleration. The answer to that is yes, Tyler. I'm not going to bother recording Wednesday's session actually, since it goes right up to Wednesday. Wait, do you guys? How much time do you guys have to take the exam? Is it a window, or do you have to take it?
Pretty sure it's open 7:30 to like 11:45.
Say that again.
We get 2 hours and 15 minutes to take it. It opens at 7:30 and then it closes at like 11:45. So you have like a small like hour window to take it
Okay.
if you like wait an hour to take it, I guess.
All right. I have 2 minutes. I am just going to run through this one real quick, and then I will save a few words at the end. So if you have to go at 5:30 sharp, that's fine. Thank you for coming. But yeah, I'm probably going to go overtime, so this is a fair warning. So, what we want to do here is apply one formula. So the question is asking for the period. Period is in units of time, and the symbol for that is t. So the period is given by the following formula, which is just one of Kepler's laws, and it follows from, I think, the conservation of angular momentum. But this is the formula. So we just need to figure out what A is, and the rest of these are known, and known things are given. So if you look at the diagram that's on the left of the gravitation, or right of the gravitation section of your equation sheet, it's got the definition of what A is. So you've got this weird looking ellipse, and then you've got like center here, and then this is a foci, one of the foci of the ellipse, and A is the distance from that to the center. So if this is a nice circle, then your A is, then the foci and the center are at the same point. Yeah, so it's a definitely confusing naming convention. But yeah, so A is this distance, not acceleration. So in this problem, when we have a nice circle, then the A is just going to be the radius of the circle. So A is this, and so we know that we're a certain distance above the Earth. So really, what we've got is A is. Here, actually, let me. So it's the radius of the Earth, which is this plus this extra little bit. So it's the height above the surface of the Earth plus the radius of the Earth. That's what A is. So radius of the Earth plus height. And then you can just plug that into the formula. Yeah, I know how to do that. So you can plug numbers into this. That's not too hard. It ends up being about 10 to the 7th. Yeah, that's right. It's close to 10 to the 7th. So you plug the numbers in. It's really not that interesting. I'm not going to bother plugging it in, but the answer ends up being 5,436 seconds. Remember, that's asking for units of seconds. That's what the problem said. They're not trying to trip you up with any conversions with that. But I think that's close to the number of seconds in a day. Not sure. But that's answer C. So yeah, really the key is figuring out what A is. All right. So that is that. We're not going to get to question 15 today, but that's okay. Does anyone have any questions before we wrap it up? M is the mass of the Earth. Mass of the satellite does not matter for the distance or for the period. And there's an intuitive way to think about that, and that's because it doesn't matter. You're going to accelerate down at the same rate, and that acceleration is the thing that's causing you to be in orbit. It's the force, but the force is the mass ends up canceling out of the force equation. So it's really the acceleration that's doing the thing that's pulling you in. So the bigger the big mass, the smaller the period. Any other questions? All right, doesn't seem like it. I am going to